Hello everybody and welcome to this A-Level Chemistry exam question walkthrough video where I'm going to be taking a look at a full AQA paper from 2021 covering inorganic and physical chemistry. Feel free to download the questions from the link in the description and have a go at it yourself. Try and keep to less than 2 hours, that's the length of this paper, then watch my video back and see how you got on. During this video, I'll be modelling my thinking behind the question in blue, and the answers that are going to get you the marks will be written in purple. This question is about enthalpy changes for calcium chloride and magnesium chloride. Part A, state the meaning of the term enthalpy change. So enthalpy change is defined as being the heat energy change at constant pressure. But for a 1 mark question like this, you could probably drop the word energy, but what's really crucial is the word heat and constant pressure. The figure shows an incomplete Born-Haber cycle for the formation of calcium chloride. For 3 marks, we need to complete the figure above by writing the formulas, including state symbols, of the appropriate species of each of the 3 blank lines. So a Born-Haber cycle shows how elements are converted into an ionic compound. And we always have our final goal on the bottom line as 1 mole of a particular ionic compound, in this case calcium chloride. And so in general, what we have is on this line, we always have the elements that make up the ionic compound. And so that means the elements calcium and chlorine. They need to be in their standard states and they need to be in a particular multiple in order to match this 1 mole of ionic compound. So actually that's quite nice and easy here because we just need 1 calcium solid and 1 Cl2 gas. And we can sort of take our lead from the line above, but it does need to be changed slightly. So calcium solid, chlorine gas. And so then this arrow, which is going upwards, that means this is an endothermic change, whereas the one going down was exothermic. This arrow, where we're changing our calcium solid into calcium gas, that is the enthalpy of atomization of calcium. And you'll notice that the chlorine, Cl2, hasn't changed. And that's one of the rules here for Born-Haber cycles. You only change one thing at a time, so you can isolate the particular enthalpy change that is occurring. And then we can see for the next line up, also endothermic, that the calcium gas is becoming calcium 1+ gaseous with an electron. So that means that this reaction was the first ionization energy of calcium because we've taken a mole of gaseous atoms and we've turned it into a mole of singly positive gaseous ions and also taken that mole of electrons away. Then we've got another blank here, and in order to work out what's going on, we could take our lead from the very top line here. And so we've got calcium single positive gas on this line. Up here on the top line, we've got calcium 2+ gas. And so here we could put in, and this is probably the best thing to do, calcium 2+ gas. And what we've done to make that change occur is we've taken another mole of electrons. This time we're taking it away from the singly positive ions. So now we've got a total of 2 electrons on this line. And so again, we haven't actually changed the chlorine. The chlorine has remained constant through each of these first 3 changes. And then on the top line, you can see that what's happened is the chlorine, which hasn't changed yet, has now atomized. Now it's atomized and produced 2 moles of chlorine gas, and so that means that we're actually atomizing 2 moles of chlorine because the definition of enthalpy of atomization is when you make 1 mole of a gaseous atom, and so we're making 2, so this arrow here is representing 2 lots of the atomization of chlorine. As an aside, this line could actually also have been the atomization of chlorine first. And if that had been the case, you could have not touched the calcium at all and atomized the chlorine at this stage and put 2Cl gas on this line, as I'm showing down at the bottom. That's an alternative for this row here, but it doesn't matter which you put in. And then the second to last arrow and the last mark that we're getting is going down from the top to here. Now, what's happened here is the chlorine atoms in the gaseous form have gained a mole of electrons each. And so this is the electron affinity of chlorine. By definition, 1 mole of chlorine gas gains 1 mole of electrons. And so this arrow is again symbolizing 2 lots of the enthalpy of electron affinity for chlorine. And then last of all, we've got gaseous ions on this line, and we've got the ionic compound down here. So this is the lattice enthalpy, this arrow. Now, since the arrow is pointing upwards, it is the lattice dissociation enthalpy. If it was pointing downwards, the lattice formation enthalpy. I've gone into a lot more detail here than you needed to for the 3 marks perhaps, but it will help us in the question that's coming up next. Table 1 shows some enthalpy data, and so you can see that all of those changes that I was talking about in the previous question are now being given some numerical values here. And our command is to use the figure in part A and the data in table 1 to calculate a value for the enthalpy of lattice dissociation of calcium chloride. There are 2 ways to answer a question like this. The first way is to add all of these values from the data table to your Born-Haber cycle that you were looking at in the previous question. So we've got the enthalpy of formation minus 795. That will go here. The enthalpy of atomization of calcium should be added in next. Then the first ionization energy, then the second ionization energy, then 2 lots of the atomization of chlorine, don't forget. So that's 121 multiplied by 2. And then 2 lots of the electron affinity of chlorine, so minus 364 multiplied by 2. And then you're trying to work out what the value for this arrow is, so starting here and finishing at the top of the arrow. And so when you use a Born-Haber cycle in this way, what you do is you move the other way around to end up at the same place. So the key thing is that we start on this line and we finish on this line. So what we end up doing is we end up going up here, so we're going against that first arrow, so that is minus 795, so plus 795. Then we're going with this arrow and this one and this one and this one and this one. And so we end up with a total for the lattice dissociation enthalpy by summing all of these numbers, and we get 2,242. The alternative method that you could use is one that relies on you remembering that the enthalpy of formation is equal to the sum of all of the other enthalpy changes in this cycle. So going from here down to here is equivalent to going all the way around the rest of the cycle. So in other words, enthalpy of formation is equal to the sum of all of the other enthalpy changes. This method relies on the lattice enthalpy being enthalpy of lattice formation, and so what that means is, since we're being required to calculate the lattice dissociation enthalpy, the value that we get will be a negative one when we use this memory aid of minus 2242, and we need to flip that sign to be the positive one because dissociation is always a positive enthalpy change. So we could run the numbers faster probably than using a Born-Haber cycle, but we do need to remember that the lattice dissociation must always be a positive number. Magnesium chloride dissolves in water. Give an equation, including state symbols, to represent the process that occurs when the enthalpy change of solution of magnesium chloride is measured. So they've done a quick switch here between talking about calcium chloride to magnesium chloride, so we need to not fall into that trap of sticking with calcium. So whenever you dissolve anything, you take the solid ionic compound, 1 mole of it, and it turns into the aqueous ions that ionic compound is comprised of. So magnesium chloride is MgCl2, and so the ions that make that up will be Mg2+, aqueous, and 2Cl- aqueous. And so that would probably be the best thing to write for our answer. We could recognise that this dissolving is likely to be an equilibrium, but you don't need to do that. And equally, you could, if you wish, include the AQ symbol on the left-hand side to show the sort of the active dissolving that the solvent is carrying out. But again, not necessary. And what I've put on the actual answer line is my preferred answer. Table 2 shows some enthalpy data. you can see that what we've got is we've got three enthalpy changes all associated with an enthalpy of solution. We've got the lattice dissociation enthalpy of magnesium chloride. Again, notice that that's a positive value. And then we've got two enthalpy of hydration values, one for magnesium gas, which is negative, and another for chloride gas, which is also negative. So hydration is an exothermic process. When you're working with enthalpy of solution, you can actually construct this like a mini Born-Haber cycle, and it only ever has three steps. You always start with your ionic compound on one line, so that, remember, is a giant 3D ionic lattice of alternating positive and negative ions, strongly held together by electrostatic attraction. Then we've got the lattice dissociation enthalpy, which is where those attractions are broken and the ions are turned into gas. And so this top line is gaseous ions. And then what you've got is this arrow pointing downwards, this exothermic reaction, which is the hydration of all of these gaseous ions that have been produced. So this is the sum of each individual hydration, and where there are more than one ion, in the case of the chloride ion, we need to double that hydration or any other multiple as appropriate. So this is the sum of the hydration values. And so this other arrow on the left, this is the actual enthalpy of solution, where we dissolve our magnesium chloride to make the aqueous ions, and it's the same aqueous ions that we produce when we hydrate the gaseous ions. And so you can see from this Born-Haber cycle that this enthalpy of solution is equal to the enthalpy of lattice dissociation plus the sum of all of those hydrations. So I've drawn this picture to help us understand it, not because it's vital for this mark, because in part E we're being asked to use our answer from part D on the previous page to calculate a value for the enthalpy of solution of magnesium chloride. And so the answer to part D was just the equation that allowed us to say that magnesium chloride was turning into aqueous ions. What's really important for this question is that we remember what I said about the memory aid, that the enthalpy of solution is equal to the sum of all of the others. So we need to take the 2493 for the lattice dissociation enthalpy, add to it the minus 1920 for the hydration of magnesium, and add to that minus 364 multiplied by 2, and then we get an enthalpy of solution of minus 155 kilojoules per mole. If you forgot to multiply the hydration of chloride by 2, you would still get one of these two marks. In F, we're told that the enthalpy of hydration of calcium is minus 1650. We're being asked to suggest why this value is less exothermic than magnesium has for its enthalpy of hydration. And so we're comparing calcium to magnesium. And so when an ion is hydrated, what happens is an attraction forms between the ion and either the hydrogen of the water or the oxygen of the water. Now, since magnesium and calcium are both positive ions, it's an attraction to the electron-rich oxygen in the water. And so what we need to do here is compare the sizes of calcium and magnesium. Now, calcium is a bigger ion and it has the same charge. And so what you could say is it's a bigger ion, or you could say it's got a lower charge to size ratio compared to magnesium 2+, or it's got a lower charge density. And so as a result of any one of those three things that we mention in M1, we can say that there is therefore a weaker attraction between the ion and the electron-rich oxygen in water. This question is about atomic structure. A. Define the mass number of an atom. Well, the mass number is defined as the number of protons added to the number of neutrons. And so these are the things that you find in the nucleus of the atom. And they're the subatomic particles in the atom that have got the mass. And so the mass number is very literal, because in chemistry the mass of an electron is taken to be 0. And so this is the number of things in the atom that have got mass. In B, complete the table below to show the numbers of neutrons and electrons in the species shown. First of all, we've got titanium 46. So the mass number is 46, so that means that the number of protons added to the number of neutrons is equal to 46. Now titanium has a mass number of 22, and so that means when we subtract that 22 away from the 46, we get 24 neutrons in the nucleus of titanium. And in titanium-49, the mass number is this time 49, and so 22 protons subtracted away from 49 gives us 27 neutrons. And then the electrons, well, for atoms, the number of electrons is the same as the number of neutrons. So you can see that the first titanium has got no charge, so equal numbers of protons and electrons, so 22. In the second one, titanium has got a 2+ charge. So since there are 22 protons, it would start with 22 electrons as well. But it's +2, which means it's lost 2 negative electrons, so the number of electrons is 20. In C, we're told that a sample of titanium contains 4 isotopes with a mass of 46, 47, 48, and 49. This sample has a relative atomic mass of 47.8. And what that means is the average mass of an atom of titanium has got a mass of 47.8. So there'll be some 46, 47, 48 and 49, but the average of them, if you had 100 of them on a balance, would be 47.8. And so that's how the relative atomic mass is different to the mass number. Mass number is always an integer, relative atomic mass is often a decimal, and we report it to 1 decimal point. We're told that the ratio of abundances of the isotopes of 46 is 2 to 2 to 1 for the titanium-49. And we're being asked to calculate the percentage abundance of titanium-46 in this sample. Now this seems strange because we've not been told anything about titanium-48, and we would instinctively think that we're being asked to work out the percentage of that, which we could do and then work backwards to work out what titanium-46 must be. But it is easier in this instance to assign each part of this ratio a letter, and let's just pick N for number. And so the ratio of titanium-46 is 2N to 2N to 1N, and then since percentages are out of 100, the abundance of titanium-48 can be taken to be 100 minus these 5 N's that we've used so far. And so when we calculate the relative atomic mass, we do this by adding together the product of the mass number multiplied by the abundance, and then add that to the mass number multiplied by the abundance of the next isotope, and we keep going on and on and on until we run out of isotopes. And then we divide it by the sum of the abundance on the bottom, which is usually a percentage, so 100, but not always. And so since we know the relative atomic mass is 47.8, we then work this out by doing 46, the mass number, multiplied by the abundance 2N, add that to 47 multiplied by 2N, add that to 49 multiplied by 1N, and then add that to 48 multiplied by this complicated looking abundance of 100 minus 5N. And then if we calculate this in stages, we have 47.8 is equal to 92N plus 94N plus 49N plus 4,800 minus 240N. And then this is all divided by 100. And then we rearrange that, and so we have 47.8 multiplied by 100, so that is 4,780, is equal to 235N plus 4,800 minus 240N, and then 4,780 is equal to 4,800 minus 5N, and so if we move the 5N over to the other side and then subtract 4,780 from both sides, we're left with 5N being equal to 20, and so N is equal to 4. And so if we return to our original abundance, which was a total of 100, which was why 48 was 100 minus N, and so that means that the abundance of 49, for instance, is 4%, because N is equal to 4, 47 is 2 lots of 4%, so 8%, and 46, which is what we were interested in, is going to be 2 times 4 as well, so 8% abundance. And remember, we might have been asked to calculate the abundance of the mass 48 titanium, and that is 100 minus 5N, so that means that is 80%. I did mention that there were two ways that you could do this. The second way doesn't work in percentages, and so it's not quite so routine as the other. What we could have done is treated the original ratio as the actual abundance, so 2 and 2 and 1. And so the difference would come in our expression here. Where we've multiplied at first 46 times by 2n, we would just multiply it by 2. And 47 would also just be multiplied by 2, 49 would be multiplied by 1, and 48 would be multiplied by our own unknown number, which we'll just call n, like before. And then the total abundance wouldn't be a percentage, it wouldn't be 100%. This time it would be 2 plus 2 plus 1 plus n. And then we would have this expression beneath, which we would then solve for n. Having done that, we would know that n would end up being 20. And so the total abundance would then become 25. And so the titanium 46 isotope is 2 out of that 25, which then is multiplied by 100, and we get 8%. And so you can see that you arrive at the same answer both methods. This method doesn't use percentages, whereas the other one did. This question is about the elements in period 3 and their compounds. Part A. When a piece of sodium is added to 200 centimetres cubed of water in a large beaker, a vigorous reaction occurs. The temperature of the water increases by 25 degrees C. Give an equation, including state symbols for the reaction of sodium with water, and suggest why it's dangerous to react a similar piece of sodium with 10 cm cubed of water in a boiling tube. Well, first of all, this equation, you've got the sodium, which starts as a solid, reacts with the water, which is of course a liquid, and that is going to be converted into the sodium hydroxide, which is going to be a solution, therefore aqueous, and the vigorous reaction is both the heating that occurs and also the gas that is evolved, because we produce hydrogen gas. And so we need 2 of all of our chemicals except for the hydrogen, which is just a 1. And then for the explanation of why it's dangerous, well, this volume, this new proposed volume of 10 centimetres cubed, is actually 20 times smaller than the original volume. And so you'd expect the temperature to rise by 20 times as much, because the energy gets spread out around the water molecules that there are. And when there are fewer water molecules, that means that each molecule will get a bigger proportion of the energy. Now, for just this one mark that there is here, we don't need to go into quite that depth. All we really need to say is that the temperature will go up more, or really in practice, the reactants are going to shoot out of that tube because the temperature, that water is all going to boil, and quickly I imagine that mixture would actually explode and the gas would shatter, and possibly even the hydrogen could ignite, because hydrogen is very flammable. And if we're producing enough energy to raise the temperature of this water by 250 degrees C, that hydrogen is probably going to set on fire. So definitely dangerous. Part B. Give an equation for the reaction of phosphorus 5 oxide with water and suggest a pH for the solution that's formed. Phosphorus 5 oxide is named for the oxidation state of the phosphorus in the oxide. And so the formula is P4O10. Because each oxygen has an oxidation state of -2, so that means -20 for all of them is being balanced by 4 lots of +5. When non-metal period 3 oxides react with water, they produce acidic solutions. And that means that we're going to have H and then something coming after it. Now, to remember these formulae, I think it's quite helpful to remember the negative ion that forms. And so phosphorus oxide produces the PO4 3- ion, so that means that the acid that is produced is going to be H3PO4. And so if you can work that out, you don't have to do quite so much memorizing. And from here, it's just a case of balancing this, because we know that the oxide is reacting with water. We know that all of the hydrogen needs to come from the water. And so we've got 4 phosphoruses in our starting reactant, which means we need 4 phosphoric acids being produced, which is a total of 12 hydrogen atoms in the products, which means we need 6 H2O in the reactants. And then the pH of this, now I've just called it phosphoric acid, that means it's going to have a very low pH, it's going to be very acidic, and so they would accept anything in and around 0. So -1, 0, +1, nothing really outside that range because it's going to be very acidic. And then part C says, explain in terms of crystal structure and bonding why silicon 4 oxide has a higher melting point than phosphorus 5 oxide. So in a situation like this, you need to talk about what the type of structure is for each of the two things that you are comparing. So silicon 4 oxide is SiO2, which is macromolecular, or you could call it giant covalent. Whereas P4O10 is molecular, or if you prefer, simple covalent molecule. That's probably the most descriptive of those two options. And so now we've established what that structure is, we now need to just compare the forces or bonds, depending on which we're talking about, that need to be overcome to melt that substance. And so since SiO2 is macromolecular, what we're overcoming is very strong covalent bonds between those atoms within the silicon dioxide. And we could also remark that these covalent bonds need a lot of energy to be broken or overcome. Whereas when we're comparing it to phosphorus oxide, these molecules will only have weak forces between them. These forces are going to be van der Waals forces between those molecules, and those forces break very easily and require very little energy to be overcome. An element in period 3 forms an oxide that is insoluble in water. This oxide reacts with sulfuric acid and with aqueous potassium hydroxide. Give the formula for this oxide and give an equation for the reaction of this oxide with sulfuric acid. Now this is a little bit of a sneaky question because there are actually two period 3 oxides that are insoluble in water, and they are silicon dioxide that we've just been thinking about, which is that macromolecular structure, and aluminium oxide. Now of those two, only one of those oxides is going to react with both sulfuric acid, in other words, the oxide can behave as a basic oxide, and with potassium hydroxide, which means that this oxide must be capable of behaving as an acid as well. Now, silicon dioxide can react as an acid, so it would react with the potassium hydroxide, but only aluminium oxide would be capable of reacting with both. And so aluminium oxide's formula is simply Al2O3. And you can work that out from the position in the periodic table and the ions that aluminium and oxygen must have. The reaction with sulfuric acid is going to be either ionic or just a full formulae equation. And so if we do the full equation first, aluminium oxide is Al2O3, sulfuric acid is H2SO4. And whenever you react a base with an acid, you always make a salt. The salt is going to be aluminium sulfate. Aluminium is 3+, sulfate is 2-, so aluminium sulfate is going to be Al2SO4 inside the brackets with a 3. And because we need 3 sulfates, we need 3 sulfuric acids, and then as a result of that, those 3 oxygen from the aluminium oxide are going to react with those 6 hydrogen from the sulfuric acid, and we're going to produce 3 molecules of water. We could do this as an ionic equation, and the only spectator ion that is present here is the sulfate ion, so we basically just strip out those SO4s, and so we're left with 6 H pluses in the place of the sulfuric acid, and 2 Al3 pluses in the space of the aluminium sulfate. Part E asks us to give the formula of a hydroxide of an element in period 3, which is used in medicine. Now there are 2 group 2 elements that are used in medicine. There is magnesium hydroxide, which is used as an antacid, milk of magnesia, and there's barium sulfate in barium meals. And obviously, since they're asking us about the hydroxide, they want magnesium hydroxide. So its formula is MgOH2. And then last of all, identify the element in period 3 from sodium to chlorine that has the largest atomic radius. Now, they've missed out the noble gas, but that's not necessarily an issue here, in fact, because the atomic radius decreases across the period for any period, whether it's period 3, period 4, period 2, and they've therefore given us the nice easy choice of we have to go for sodium. The group 1 element in any period will have the largest atomic radius of that particular section of the period. This question is about iron and its ions. we've been asked to discuss the role of iron as a heterogeneous catalyst in the Haber process. The equation for the Haber process is shown here. 3 molecules of hydrogen is reacting with 1 molecule of nitrogen, will reach equilibrium, and we're going to have 2 ammonia being produced as a result. And we've been commanded to include 3 things in our answer, and this question is worth 6 marks. So, as a rule of thumb, we could think of this as being worth 2 marks per section, and that's approximately correct. The first bullet point tells us to explain the meaning of the term heterogeneous catalyst. Now, there's 2 words to this phrase, so we need to explain both of them. Starting with the easier of the 2 words, a catalyst is something that speeds up a reaction and is left unchanged by that reaction. So that is the definition of a catalyst. And you might also say that it will lower the activation energy by providing an alternative pathway, but the first part is the most important part. And then the term heterogeneous, that means that this catalyst that we've mentioned is in a different phase or different physical state to the reactants that it is catalyzing. The second command is to explain how iron specifically acts as a heterogeneous catalyst. We've been asked this question in the context of iron, but you could almost take everything that I'm about to say and drop it into the description of any heterogeneous catalysis. And so the iron surface is going to adsorb the hydrogen and nitrogen, those reactants, onto it. And so adsorb is a really similar word to absorb, which is what obviously things like sponges do, but adsorb is specific to the thing just sticking to the surface of this substance, not going deeper into it, which is what happens with water in a sponge. So adsorption just sticks to the surface. Once they are on the surface of the iron, the bonds in those reactants are going to weaken and the reaction is going to take place. And then finally, the products that are made are going to leave the surface of this iron, and that process is actually called desorption. And then finally, we're being commanded to explain the factors that affect the efficiency and the lifetime of the catalyst. And there's really 2 parts to this. The efficiency is determined by the amount of surface that this iron has to enable it to act as a catalyst. So a large surface area is going to increase the efficiency, perhaps by using a small powder or pellets of our iron. Or maybe we might have some kind of support medium, which is typically a mesh or a honeycomb, and we get that in the catalytic converters, if you remember the catalyst that's present there. Now, the lifetime of the catalyst and its efficiency, actually, can both be affected if the catalyst is poisoned. Now, specifically in the Haber process, the poison is sulfur. And what the poison does is it binds to the catalyst in a particular region which is called the active site, and that active site then gets blocked. And we can use the term active site here in the same way that we use it when we're talking about enzymes, because remember, enzymes are considered to be biological catalysts. And so there are 3 discrete sections to my answer as I've structured it here. Each of those sections is important, and as I said before, we can consider that to be worth 2 marks per section. In part B, we're still with catalysis. It says Fe2 plus ions catalyze the reaction between the peroxodisulfate ions and iodide ions in aqueous solution. And we're shown the equation here. This is the peroxodisulfate, this is the iodide ions, they're both aqueous, and we make sulfate ions as our product and iodine. We're asked to explain why this reaction is slow before the catalyst is used, and to give 2 equations to show how the Fe2 plus ions catalyze this reaction. Well, first of all, and quite simply, these 2 ions are negatively charged. As a result of that, they're going to repel each other. As a result of that, the activation energy is high. What that means is these ions are only going to come into contact with each other if they have sufficient energy to overcome the repulsion between them. And that's enough for 2 marks, 1 for each of those bullet points. And then in terms of the equation, this is really clever how the iron acts as a catalyst, because if you think about what's happening in this reaction, the iodide is beginning as a -1 oxidation state and the iodine is becoming 0. So that means that the iodide is being oxidized. It's giving away some electrons. And that must mean that the sulfur is being reduced. And it is. We've got -16 in total for those oxygens, and these sulfur are balancing that out. And so that means that the sulfur must be beginning as +7 each, both of them at +7, and they're both finishing at +6 in the sulfate. So each of them is gaining 1 electron, and each iodide is losing 1 electron. And so effectively, the sulfur needs to gain the electrons from the iodide, but it doesn't want to go near to it. And so what the iron 2+ does is it comes along and it donates an electron to the sulfur in the peroxide disulfate, and then it goes over to the iodide and gets an electron back from the iodide, and therefore overall the iron hasn't changed. It's gone from +2 to +3 and then back again. And in terms of the equations that we write, we need to show the Fe2+ reacting with the peroxide disulfate. Remember, each of those sulfurs needs to take 1 electron, so that means we're going to need 2 Fe2+ to do this, and we're producing 2 sulfate ions and therefore 2 Fe3+ ions. And then those 2 Fe3+ ions both need to gain an electron back, and they gain each of them 1 from each of the iodide ions in the original equation, and so then they return to being Fe2+ and I2. And what you can see is if you were to add these two equations together like a simple simultaneous equation and then simplify what's present on both sides of these new kind of sum equation at the bottom, then we get rid of the Fe from both sides of the equation for both forms of the 2+ and 3+ that we've got. And we see that that equation simplifies down to the one that we had at the beginning, which is why the iron is said to act as a catalyst, because it is playing a role, but it is not changed as a result of the process, and it can keep going again and again, repeating those transitions that we have down at the bottom between 2+ and 3+ and back again. Give a reason why zinc 2+ ions do not catalyse the reaction in part B. This is simply to do with the fact that zinc does not have a variable oxidation state. And so that means that zinc 2+ could not be oxidised to zinc 3+ because zinc can only be 2+ as an ion. So it only has one oxidation state. Part D. Iron reacts with dilute hydrochloric acid to form iron 2 chloride and hydrogen. And here is the equation, and this is the iron chloride and the element iron. We're told that we've got a 0.998 gram sample of pure iron, and it's added to this volume and concentration of hydrochloric acid. One of these reagents is in excess, and the other reagent limits the amount of hydrogen produced in this reaction. Calculate the maximum volume in meters cubed of hydrogen gas produced at 30 degrees C and 100 kilopascals. Give your answer to 3 significant figures. In your answer, you should identify the limiting reagent in this reaction. Even though the first command we were given was to calculate the maximum volume of hydrogen, we actually can't do that until we know which of our 2 reactants is the limiting reagent. And so, since the iron is a solid, we need to work out the moles of iron by doing mass divided by relative atomic mass. So 0.998 divided by 55.8 gives us 0.0179 moles. And then for the HCl, we do concentration, 1 multiplied by volume, 30 divided by 1,000, because that needs to be in dm cubed, and that gets us 0.03 moles of HCl. And so when we compare those 2 numbers, at first glance, the iron looks like it is limiting because it is the smaller of the 2 numbers. But we need double the number of moles of HCl that we've got for iron. And we don't have double the moles. We have bigger, but not enough for it to be double. And so that means that the HCl is the limiting reagent. And so moving forward, the moles of hydrogen gas that we can produce has to be dependent on the moles of HCl that we started with. And when we compare the equation, we can see that there are 2 moles of HCl required for every 1 mole of H2 that we produce. So that means that the moles of H2 that we're going to produce needs to be half the moles of HCl that we calculated earlier. So in other words, 0.0150 moles. To calculate the volume of hydrogen, we need to use the ideal gas equation, and that was signposted by the fact they gave us the gas constants value here. And in order to do that, we use PV equals nRT, and we've been asked to calculate the volume, and so that means we're using nRT divided by P, the pressure. Before we use that, we need to check that our units are in the correct format, and they're not. So that means that we need to convert our 30 degrees C temperature into Kelvin, which is 303, and we need to convert our 100 kilopascals into just pascals, so that is 100,000. And we use our moles that we've just calculated in part 4. And so then, when we crunch our numbers into the equation, we put the 0.015 multiplied by 8.31 multiplied by 303 on the top. We divide that by 100,000 and we get a volume of 3.78 times 10 to the minus 4. No further conversions necessary. This value from the ideal gas equation is already in cubic meters, and so we don't need to do any conversions on this occasion. The figure below shows some reactions of iron ions in aqueous solution. And if we take a look at this, we are looking at iron 2+ at first, with 6 water molecules acting as ligands around in the complex ion. And we know that this is the typical iron-containing substance in most solutions for iron 2+. And we can see that it's reacting with sodium carbonate to make a precipitate A. It's in the presence of the air, it's turning into the same looking complex ion, but it is 3+. And then that 3+ compound reacts with sodium carbonate and produces precipitate B, which presumably is different. So identify A and state its colour. So that's the first precipitate. Now, when sodium carbonate interacts with complex ions, if it is a 2+ ion, whatever the metal is, we're going to make the carbonate as a product. So the identity is iron 2 carbonate, or FeCO3. This is a green coloured precipitate. Mostly all of the colours to do with iron 2+ are in fact green. Give the formula of B and state its colour. So this time we're not going to make iron carbonate because the iron 3+ has a greater acidity than the iron 2+. So that means it's able to interact with the carbonate as an acid would. And so when an acid reacts with a carbonate, we end up producing carbon dioxide and water, and that's what's going to happen here, and we need to incorporate that into our equation. And so when any metal 3+ solution reacts with a carbonate, what you produce is a precipitate of that metal hydroxide. And so what happens is the carbonate, a base, removes 3 of the hydrogen atoms from 3 separate water ligands in this substance. And so what that means is we end up producing the hydroxide, which is going to be FeH2O3OH3. And those aren't separate OHs that have joined the iron. What they are is 3 OHs that used to have, each of them, 1 extra hydrogen, and they used to be water, but now they are hydroxides. Sometimes you can write FeOH3 just by itself, but I would recommend writing it with the 3 water in as well. The colour of this precipitate is a brown colour. It's sometimes referred to as a rusty brown colour, and iron 3+ is actually the active iron ingredient in hydrated iron 3 oxide, but I wouldn't overcomplicate it when it comes to naming colours. Keep it simple. This iron hydroxide is going to be brown. And then the ionic equation, the reason that they ask for an ionic equation is basically saying, I don't want you to mention sodium in this reaction. Everything else is going to be as you would expect it. And so we start with our iron-water complex, 3+. It's reacting with carbonates, and we're going to make our iron hydroxide product, and we're going to make water, and we're going to make carbon dioxide. And sadly, we need to also balance this equation in order to get any credit at all. And so as we're making carbon dioxide, we need to make as many carbon dioxides as we're using carbonates. in order to turn each carbonate into water and carbon dioxide, that carbonate needs to accept 2 protons. And so since the initial ion complex needs to lose 3 hydrogen ions, then we need to have a common multiple here of 6. So 2 of those ion complexes would need to lose a total of 6 hydrogen atoms. Those would be gained by the 3 carbonates, and so therefore we need to have a 2 and a 3 for our reactants, which means we need a 2 for our ion complex, and we're going to make, for each 3 of those carbonates, we're going to make 3 water and 3 carbon dioxide. And you could have multiples of this if you'd sort of overbalanced it, but it needs to be 2, 3, 2, 3, 3, or some direct integer multiple of that. In the final part to this question, we've been asked to explain why an aqueous solution containing iron 3+ ions has a lower pH than an aqueous solution containing iron 2+. So I've already said that that's the case. You would expect it to be a stronger acid than the iron 2+, but this question is asking us to dive into why. And the reason is that the iron 3+ is going to be smaller than iron 2+, and so as a consequence of that, the iron 3+ is going to have a greater charge density, or a charge to size ratio. I prefer saying charge density. As a consequence of that, the iron 3+ ion is going to be more polarizing. And so to actually form the complex altogether, remember, the water needs to donate a pair of electrons to the iron, and that forms a coordinate bond. And so the iron 3+ polarizes this water molecule more than the iron 2+ does. And so as a consequence of that, that weakens this O to H bond within the water ligand. And so that means it will break more easily. And as a result of that, this weakened bond is therefore going to release more hydrogen ions than the corresponding water ligands do in the iron 2+ complex. And so, as a result of that, more hydrogen ions means a stronger acid and therefore a lower pH. This question is about the equilibrium shown here. On the left-hand side, we've got 2 moles of SO2 gas and 1 mole of oxygen gas, and then we're shown that it's a reversible reaction, and we've got 2 moles of SO3 gas. State and explain the effect, if any, of a decrease in the overall pressure on the equilibrium yield of SO3. This is a really common question, and I actually feel that it's easier to tackle the explanation part and arrive at the effect once you're happy with your explanation. And so obviously this is to do with Le Chatelier's principle, which covers the idea that the equilibrium is going to shift to oppose the applied change. And since we're decreasing the overall pressure, the equilibrium is going to shift to increase the pressure, and that will be the first explanation mark. And then we need to inspect the equation and decide which side will have the higher pressure. And so since there are 3 moles on the left-hand side and 2 moles on the right-hand side, the left-hand side will have a higher pressure because more moles of gas means higher pressure and fewer moles of gas means less pressure. And so since we're saying that the equilibrium is going to shift to raise that pressure back up, that means it will shift to the left-hand side because there are more moles on the left-hand side. And then now we can go back to our conclusion, which is the effect, which is that since it is shifting left, that means it will be using up the SO3 to create those things that are shown as reactants, and so the yield will decrease. In part B, we're told that a 0.460 mole sample of SO2 is mixed with a 0.25 mole sample of O2 in a sealed container, that means it's a closed system, at a constant temperature. When equilibrium is reached at a pressure of 215 kilopascals, the mixture contains 0.180 moles of SO3, and we're commanded to calculate the partial pressure in kilopascals of SO2 in the equilibrium mixture. Well, first of all, what we need to do is we need to work out what the equilibrium moles will be for these chemicals. And so I would do this in an exam, I'd do this probably in and around the equation at the top here, but I'm going to write the equation out again. And then we're going to work out what the initial moles are, so that's what the I on the left-hand side is showing. So we've got 0.46 of SO2, 0.25 of O2, and since we've not been told anything about it, we assume that we've got 0 moles of SO3. And then I always leave a little bit of a space, which I'll come back to in a moment, and I work out what the equilibrium moles are going to be. So we know that SO3 at equilibrium is 0.18 moles. And that's the key to unlocking the rest of the values. We started with 0 moles of SO3 and we've gone to 0.18 moles of SO3. So that has increased by 0.18. So that is the change. And so I always put a C on the left-hand side for the change. Now, since the coefficients in this equation are 2 to 1 to 2, that means that the SO3 will go up the same amount of moles that the SO2 went down, so namely 0.18. So that means that the SO2 will go down 0.18 from 0.46, and so it will end up at 0.28 moles. And that will actually be our first mark here, but we've done a lot of the thinking. And then since the coefficients, the ratio of SO2's decrease to oxygen's decrease is 2 to 1, that means that oxygen will only go down by half as much as the SO2 went down. So in other words, it will decrease by 0.09. And so we will end up with 0.16 moles of oxygen at equilibrium. And so that will be our second mark. Next, we have to remember that all gases behave ideally. So in other words, the pressure that they exert on their container is directly proportional to the number of moles that there are. So in other words, in our mixture, we've got a certain number of moles of each of our 3 gases, and together those 3 moles are giving us a pressure of 215 kilopascals. And so to calculate what the partial pressure is, we need to work out what fraction of the total moles our particular gas is, so specifically our SO2. And so what we're going to do is we're going to work out what our mole fraction is. And so to do that, we need to work out what the total equilibrium moles is by summing our 0.28, 0.16 and 0.18, and that gives us an answer of 0.62 moles. That will be mark point number 3. And so the SO2 mole fraction is 0.28 out of our total 0.62. And we don't actually need to calculate this value, because what we're going to do now is we're going to multiply this fraction by the total pressure, 215, to arrive at the partial pressure for SO2. And this gives us an answer of 97.1 kilopascals, or 97 kilopascals. The precision isn't too important because we haven't been told to give a particular number of significant figures, although all of the data given so far is to 3 significant figures. So 97.1, probably slightly better. A different mixture of SO2 and oxygen reaches equilibrium at a different pressure. The table below shows the partial pressures of the gases at equilibrium. Give an expression for the equilibrium constant Kp for this reaction and calculate the value of the equilibrium constant and give its units. So the expression for Kp tells you a numerical value that is the relationship between the partial pressure of the products compared to the reactants. So to construct this, what we always need to do is we need to refer to the equation. So I've rewritten that along the top. And so you always take the products and put that on the top of the expression. And so you write the partial pressure of SO3. Now the coefficient in the equation is a 2 in front of the SO3, so this needs to be squared. I usually like to put brackets around the partial pressure term when I'm squaring it in particular, just so I can get that differentiation between the 3 of the SO3 and the 2 for the squared. And then we put the reactants on the bottom, and so the reactants are the SO2 and the O2, so we put the partial pressures of each of those, and since the coefficient for SO2 is also a 2, this value needs to be squared as well. So then that's the expression, that's the first mark. Then we substitute these values in, then we run the calculations, and we get a value for Kp of 1.20 times 10 to the minus 2. 1.2, absolutely fine. No significant figures have been specified here. And then the units, we've got two partial pressure terms on the top, so that's kilopascals multiplied by kilopascals. And we've got three partial pressure terms on the bottom, so that's kilopascals 3 times along the bottom. These will obviously simplify down. The first two will cancel, then the next two will cancel. And so we're left with 1 divided by kilopascals. We always have to have the units on the top line, so we bring them from the bottom line up to the top. When we do that, we invert the powers. So kilopascals on the bottom of the expression becomes kilopascals to the -1 on the top. And so that's the units for this particular KC expression, kilopascals to the -1. And then in part D, the final bit of this question, we are asked, what is the effect on the value of Kp if the pressure of this equilibrium mixture is increased at constant temperature? And so actually this is a really fast question because the only thing that affects the actual value of Kp is temperature. It might increase it, it might decrease it. That's something that we have to decide on a case-by-case basis. But when we're asked about a change in pressure, the answer is no effect on the value of Kp. And that's the same for changing concentration and changing catalysts as well. The reason that Kp will not change is if we increase the pressure, what that will do is that will proportionately increase the partial pressure. Now, since there's more terms on the bottom of this expression than on the top, we might think that Kp should decrease. But the equilibrium is going to shift to respond to this pressure increase. And so it will actually shift to the right-hand side. And what that will do is that will increase the partial pressure of SO3. And so we might think that the Kp value should increase as a result of that conclusion. And actually what happens is those two consequences will cancel each other out perfectly and arrive at us having no overall effect on the value of Kp. And so the correct answer is that Kp will stay the same. Pure water dissociates slightly, as shown by this equilibrium. We've got water on the left, then we've got the reversible reaction symbol, and then we've got hydrogen ions and hydroxide ions on the right-hand side. We've got the enthalpy change symbol showing us it is positive, so endothermic. The Kc expression is shown here for the equilibrium constant. We've got the products on the top with square brackets, which means concentration, and then reactants on the bottom. And then the ionic product of water, Kw, is shown here as H plus concentration multiplied by OH minus concentration. In A, we are asked to explain why the water concentration is not shown in the Kw expression. So remember, these concentration values are equilibrium concentrations. So if we imagine before that equilibrium was established, let's say we had 1 billion water molecules, such a small number of those molecules dissociate, let's say 2, and then we've got at equilibrium 2 less than 1 billion water molecules, and we've got 2 hydrogen ions and 2 hydroxide ions. And so the concentration of water is effectively a constant. And certainly we can say that it's very large in comparison to the hydroxide ions and the hydrogen ions. And so as a result of that, the Kw incorporates the water concentration into it. It's kind of taken as the product of Kc multiplied by the concentration of the water. And so this equilibrium very much lies to the left-hand side of the expression, really significantly so, as you can see from the Kw values in the next question. So we only need to say one of these options that I've been putting with the forward slashes, but they all kind of add together to give the full picture, but only one of them for that 1 mark. And then we're shown in table 1 how temperature increases affect the value of Kw. And we've been asked in part B why the value of Kw increases as the temperature increases. And so the first mark for this is to say that the forward reaction in the equilibrium is endothermic, as we can see from the given value here. Sometimes you're not given this value and you're just expected to know that a dissociation requires energy, so is endothermic. And so as a result of that endothermicity, the equilibrium will shift to the right-hand side when the temperature is increased, which gives us a greater concentration of hydrogen ions and hydroxide ions, and so the value of Kw will be larger. In C, we're asked to give the expression for pH, then to calculate the pH of pure water at 50 degrees, and we're commanded to give the answer to 2 decimal places. That's standard for pH values because it's a log scale and the 2 decimal places are important. Then we're asked to explain why water is considered neutral at 50 degrees C. Firstly then, the expression for pH is that pH is negative log to the base 10 of the hydrogen ion concentration. And to be honest, we don't need to put the base 10 here because that's sort of a requirement of a maths paper. In chemistry, we assume that when you write log log, we mean log to the base 10. And then for the calculation, because this water is pure, the hydrogen ion concentration is going to be equal to the hydroxide ion concentration. So Kw is the product of those 2 numbers. And so what we can do is we can substitute in H plus for the OH minus. And so we're left with Kw is H plus squared. And what that means is that H plus is equal to the square root of Kw. And at this temperature, 50 degrees C, the Kw value that we need to use is 5.48 times 10 to the minus 14, unlike at room temperature where the value is different. 1 times 10 to the minus 14 is what we take for standard Kw values if you've not been told anything different, but here we need to use this value for Kw. And so we need to take the square root of 5.48 times 10 to the minus 14. That gives us the H plus concentration, and then the pH is going to be the negative log of this value, which gives us 6.63 to 2 decimal points. And then we've been asked to explain why this is still considered neutral, because it isn't pH 7, and this is actually what I've already said. The hydrogen ion concentration is equal to the hydroxide ion concentration. And that makes sense if you consider the dissociation of a water molecule. For every bond that breaks between the oxygen and one of the hydrogens, what you're going to end up with is 1 hydrogen ion and 1 hydroxide ion for each dissociation that occurs. So that's why these concentrations are taken to be equivalent. A pH meter is calibrated using a calibration graph. To create this calibration, a pH meter is used to measure the pH of separate solutions, each with a known accurate pH. They would probably use a range of different buffer solutions to do this. And so what you would have is you would have the true pHs, that's the pHs of the buffer solution that you've used, and then you would record the value on the y-axis that your pH meter is reporting, and then you would plot this as a graph which you would expect to be a straight line. And then what you would do is you would use the measured pH meter reading to determine what a true pH value is for something that you don't have a buffer solution for. And that's what you're being asked to do in part D. We've been asked to use figure 1 to give the true pH, that's the x-axis value, when the pH meter reading, the y-axis value, is 5.6. So we need to read up the y-axis, find 5.6, so that's just here. Then we construct a line along to here, and then we read down to the x-axis, and we get 5.5. You'd typically be allowed to be half a square out. I think if you're going to be out, you're going to be slightly above 5.5, so you'd probably be allowed 5.5 or 5.6. And then in E, you've been asked to suggest why the pH probe is washed with distilled water between each of the calibration measurements. You'd probably have at least 3 different calibration measurements to construct this graph. And the idea here is that you don't want any residual solution or substance which could interfere with your reading. So if you've just dipped your probe into pH 4, you don't want to have some of that buffer left on the pH meter when you move on to pH 7, for instance. And so you need to communicate the idea that different solutions must not contaminate each other. The calibrated pH meter is then used to measure the pH during a titration of hydrochloric acid, strong acid, with sodium hydroxide, a strong base. And we're asked here to explain why the volume of sodium hydroxide added between each pH measurement is smaller as the end point of the titration is approached. And so the idea here is that you don't want to miss the end point. If you add it in 2 cm cubed portions at a time, which you probably would early on during this titration, then you're very likely to overshoot. And so what you would probably do is go up in 2s early on, then maybe 0.2s, closer to the end point, and probably 0.1s at the last minute. And so you don't want to miss the end point, because that's where there is this large change in pH. And so that's when you want your pH to be detected. You want to notice this point, and if you were using an indicator, you'd want it to change colour during this region of the curve. And during this titration, you would collect the data and you would plot a graph, and this is the graph that we would expect. And so you can see that we're using hydrochloric acid because it's a very low starting pH, below 1 by the look of this y-axis value. And you can see that sodium hydroxide is a strong base because we're finishing with a pH of something like 13 when you've got an excess of sodium hydroxide. And the end point that I was mentioning, that point where the pH dramatically increases, that is at about 25 cm cubed from this graph. And then table 2 shows some data about indicators. We've got 3 different indicators, and we're told the pH range over which they change colour. And then we've got the colour in low pH and the colour in high pH for each of them. And the student is planning to do the titration again using an indicator to determine the endpoint, presumably rather than the pH probe. And we're asked to state why all 3 indicators are suitable for this titration. And the suitability of an indicator is determined by whether it changes colour at that rapid pH change that occurs at the endpoint. And the answer must be that that is what they do. They all have their colour change, which coincides with this steep or this vertical region of the titration curve. And we can prove that if we find their range on the graph. And so bromocresol green changes colour at pH 3.8, which is about here, up to about 5.4, which is around about here. So it's towards the bottom end of this vertical region, but it is still acceptable. It would be yellow at first down here, and then turn to blue thereafter. And then phenol red could similarly be used. This was very obvious that this one can be used because 6.8 to 8.4 is this region here, almost in the middle of the vertical region. And then thymolphthalene, which is like phenolphthalein but not quite the same chemical structure, that is at the very top end of acceptability because it starts to change colour at 9.3 and finishes at 10.5, which is just before this vertical region starts to level out. So if you were asked to select an indicator, the safe bet is phenol red in the middle, but since they've told us that all 3 are suitable, then we know that it's all about the fact that they change colour in this vertical region. And then finally for this question, we're asked to do another calculation. We're told that we've got a certain volume and concentration of sodium hydroxide solution added to 25 cm cubed of a certain concentration of hydrochloric acid, and we're asked to calculate the pH of the final solution at 25 degrees C. And we're told the Kw value at 25 degrees C as well. And when you're told a Kw value, when you've been commanded to calculate a pH, that's really a bit of a clue that the final pH is going to be a basic pH above 7, because if it wasn't, then you wouldn't need the Kw at all. But I could imagine that they might try and trip you up, but that would be very, very rare. And so what you have to do here is you have to work out the amount in moles of each of these 2 reagents first. And so the sodium hydroxide is 36.25 multiplied by 0.2 divided by 1,000 because we need our volumes to be in decimeters cubed. And that gives us 7.25 times 10 to the minus 3 moles. And then the concentration of hydroxide ions would be the same since there is 1 hydroxide for every sodium hydroxide. And then similarly for the hydrochloric acid, the amount in moles would be 25 divided by 1,000 multiplied by 0.15. So that's 3.75 times 10 to the minus 3 moles of that, which again will be the same as the moles of hydrogen because this is a monoprotic acid. So that would just be 1 mark there for the 2 starting moles. And we can tell by inspecting these numbers that the hydroxide ion is indeed in excess, which means this pH at the end is going to be above 7. We need to calculate the moles of excess hydroxide by literally just working out the difference between those 2 numbers, and that gives us 3.5 times 10 to the minus 3 moles of hydroxide. And then we need to think about where we're going next. We are ultimately ending up calculating a pH, which means that our penultimate step needs to be to work out the hydrogen ion concentration. And since we're using a base now, we know that the base is in excess, and that means we are using the Kw expression, and so Kw is H plus multiplied by OH minus, and so there H plus is equal to Kw, which we've been given, divided by the hydroxide ion concentration, which tells us that mark number 3 must be to work out what that hydroxide ion concentration now is. So we know the moles because we got that in mark number 2, and so we have to work out concentration by doing moles divided by volume. The volume is the sum of the two volumes of solution that have been added, because that hydroxide ion will be spread out in amongst this total volume, which is going to be 61.25 cm cubed. It won't stay in its initial volume that it was in. It's going to spread out over all of that. And that gets us a hydroxide ion concentration of 5.71 times 10 to the minus 2. And then we plug that into our Kw expression by dividing 1 times 10 to the minus 14 by the answer that we've just got. And that gives us 1.75 times 10 to the minus 13, which is a really small number, which tells us we're going to have quite a large pH as a result of that. And then we need to plug that into our pH expression, so negative log of the hydrogen ion concentration that we've just got gives us a final answer of 12.76, which I do recommend giving to 2 decimal points because that's a really good habit to be in for pH calculations. But actually, when the pH is greater than 10, they're usually quite forgiving and allow it to be to 3 significant figures, which is 1 decimal point when the value is above 10. So 12.8 would still get you that 5th mark here, but I recommend 2 decimal points for those good habits. This question is about thermodynamics. Consider the reaction shown. We've got 2 moles of aluminium oxide, which is a solid, reacting with 3 moles of carbon, also a solid, and it turns into 4 moles of aluminium, still a solid, and 3 moles of carbon dioxide, this time that is a gas. And we've been given some thermodynamic data here for our 4 substances along the top row. We've been given enthalpy change values in kilojoules per mole, and the enthalpy change values are enthalpy of formation. You can tell that from the little subscript here. As a result of it being enthalpy of formation, we can see that we've got 2 zero values for aluminium and carbon. Those are our 2 elements. By definition, the enthalpy of formation for an element is 0, because the enthalpy of formation is when you make a mole of something from its elements. So you can't make a mole of carbon from a mole of carbon and expect that to have any enthalpy change, because we aren't actually changing anything. And so that's the same for aluminium. The enthalpy change for formation for elements is 0. And then on the bottom row, we've got entropy change, and that's in joules per Kelvin per mole. And the fact that we've got joules and kilojoules is going to cause us a problem that we're going to need to solve later. Part A says, explain why the standard entropy value for carbon dioxide is greater than that for carbon. This comes down to the state symbols. Entropy is almost synonymous with disorder. Not quite, but you can think of it like that. And so the more disordered something is, the more entropy it will have. And so a solid, which is what carbon is going to have much less disorder and so much less entropy than carbon dioxide gas or any gas. And so what you would need to say here is quite simply that carbon dioxide is a gas which is more disordered. Then part B says, state the temperature at which the standard entropy of aluminium is 0 joules per Kelvin per mole. Well, the fact that they're asking about aluminium is actually a little bit of a decoy here, because the temperature at which aluminium has an entropy of 0 is the same for literally every substance in the world. By definition, the entropy of any substance will be 0 at absolute 0 temperature. In other words, 0 Kelvin or minus 273 degrees C. Because by definition, at this temperature, all of the particles will be absolutely stationary, not even vibrating a tiny bit. There is no movement of these particles, and so there is no disorder, and so the entropy is set at 0 by definition at this temperature. Part C says use the equation and the data in the table to calculate the minimum temperature in Kelvin at which this reaction becomes feasible. And so this is a 7-mark question, so there's going to be quite a few different things to do here. So feasibility is ascertained from the equation for Gibbs free energy, which has got delta G is equal to delta H minus T delta S. And so this free energy, if it is less than or equal to 0, the reaction is going to be a feasible reaction. And then the reaction becomes feasible when delta G is equal to 0. And so what we get for our expression then is delta G equals delta H minus T delta S rearranges to, when delta G is 0, 0 equals delta H minus T delta S. So delta H equals T delta S, and so delta H divided by delta S is equal to the temperature T in Kelvin. And so it's clear now what we need to do next. We need to calculate the temperature as our final answer. So to do that, we need to work out delta H, which is of course the enthalpy change for this reaction, and delta S, which is the entropy change. Now, because we're using enthalpy of formation data, the enthalpy change for this reaction is the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. And so what we need to do here then is look at our products. We've got 4 aluminium. Remember, we've already said that the element is going to have an enthalpy change of 0, so we can basically ignore that. But carbon dioxide is minus 394 kilojoules per mole, and so we need to triple that because of the coefficients in the expression. And then we're subtracting from that the enthalpy of formation of the reactants. Again, carbon, the element is 0, so we're just looking at the minus 1669 from aluminium oxide, but again multiplying it by this coefficient of 2. Once we crunch these numbers, the enthalpy change for this reaction comes out to be 2,156 kilojoules per mole, so an endothermic reaction. And then when we look at the entropy change is calculated in the same way that we use enthalpy of formation actually, and that will always be the case for a Gibbs free energy equation. The entropy is the entropy of the products minus the entropy of the reactants. And this is a little bit of a longer calculation because we don't have any 0 values. So we need to take the aluminium's 28 and multiply it by 4, add it to the 214 for carbon dioxide multiplied by 3. That is the sum of the entropy of our products. And the sum of the entropy of the reactants is 2 multiplied by 51, and then 6 multiplied by 3. And when we calculate that, we get an entropy change of 634 joules per Kelvin per mole. So definitely an increase in entropy as this reaction happens. Now we've got these two numbers, the temptation would be to put these numbers straight into the delta G expression, but we must do one extra thing before doing that, because enthalpy is in kilojoules per mole and entropy is in joules per Kelvin per mole. So we need to divide our entropy change by 1000 to get them both into kilojoules. And so 634 divided by 1000 is 0.634 kilojoules per Kelvin per mole. And then last of all, we need to calculate our temperature. So we can put in our enthalpy change exactly as it was, 2,156 kilojoules per mole, divided by our entropy now in kilojoules per Kelvin per mole of 0.634. And we get a final answer to two significant figures of 3,400, or it comes out to maybe 3,401 Kelvin for a little bit more accuracy. And that's what we need to do for our 7 marks. Each of these steps will get us 1 mark each. and we will get transferred error if we make a mistake partway along, or for instance, if we forget to divide our answer by 1000, we would lose the penultimate mark, but probably get the final mark. And it's really important, therefore, when we're looking for method marks, to structure our calculation clearly so the examiner can see what we've done and can give us method marks if we don't get that final answer correct. This question is about electrode potentials and electrochemical cells. State the meaning of the term electrochemical series. Well, they've actually given us an example of an electrochemical series here. And an electrochemical series is where you show a series of electrode potentials in a particular order, a numerical order. And so that's one of the things that we could say for the 1 mark here. Alternatively, we could remark on the fact that we've got a series of half equations, and these half equations are shown in order of their electrode potential. Either of those is fine for the 1 mark. B says, state 2 conditions needed for the following half equations to have an electrode potential of 0.0 volts. Now there's only 1 mark here, so we need both of them for that 1 mark. There are 3 standard conditions, if you remember. One is for temperature, and that's one of our options that we could say here, 298 Kelvin or 25 degrees C. I prefer stating that as Kelvin. And then we've got an aqueous solution of hydrogen ions. And so another condition is for concentrations. The hydrogen ion concentration needs to be 1 mole per decimeter cubed. And then the final condition, we've already got our 2 that we need, is for gases. And there is a gas here, so it is appropriate to say that the pressure for the hydrogen gas needs to be 100 kilopascals. The next question asks us to identify the weakest reducing agent in the table above. Well, all of the half equations in this table are written in the forwards direction. And so that means that the chemical on the left-hand side gains electrons from something. And thereby, these things on the left-hand side are the oxidizing agents because they take the electrons from something else. And that means that the things on the right-hand side must be the reducing agents because they move backwards and generate electrons which they donate to something else. And so we're choosing from something on the right-hand side. Well, the electrode potential value tells us a measure of how good at going in the forwards direction these half equations are. So in other words, how good at taking electrons they are. So the larger number is the one that is best at moving forwards and therefore best at taking electrons. And so it follows that the larger number will have the chemical that is worst at going backwards. In other words, worst at donating electrons, or most importantly, worst at reducing. And so that means that this chemical with the largest electrode potential is the worst at going backwards. And so this cobalt with 6 water molecules in a complex ion will be the worst reducing agent. And correspondingly, if we'd been asked for the best reducing agent, it would have been the iron at the top. And the worst oxidizing agent is here, and the best oxidizing agent is here. Part D says use half equations from the table to deduce an equation for the reduction of VO2 1+ to turn into VO2+ in aqueous solution by iron. So we first need to identify the half equations that they're asking us about, and that is definitely this one with an electrode potential of 1. And iron appears in this top equation with an electrode potential of minus 0.44. And so what's going to happen is the vanadium half equation will move forwards and the iron half equation will move backwards because the iron has the smaller electrode potential. Now there's a trick here because the iron turns into this iron complex ion, FeH2O6 2+. And the trick comes because that same chemical appears lower down, and it has still got a smaller electrode potential than vanadium's. And so this half equation will also go backwards. And so our final iron-containing product is actually going to be FeH2O 3+. And so what that means is, overall, as a half equation, the iron is losing 3 electrons. And since the vanadium is only gaining 1 electron, we need to multiply vanadium's half equation through by 3 and then add that to the iron half equation. When we do that, we see that we've got 3 electrons on both sides of the two half equations. We also see that there are 6 water reactants in iron's half equation and 3 water products in vanadium's. And so what that translates as, we need 3 water molecules in the final overall equation as our reactant. And so finally we've got 3VO2 1 plus 6H plus Fe plus 3H2O turns into 3VO2 plus the FeH2O6 3 plus complex overall. And that's 1 mark for recognising that we're making Fe3 as a product, and 1 mark for the correct overall equation that I'm showing on the line here. Use data from the table to explain why cobalt with 6 waters with a 3 ion will undergo a redox reaction with the iron 2 complex ion with 6 water ligands. Give an equation for this reaction. Well, the explanation comes from the electrode potential values. The cobalt complex with a 3 charge is down here on the left-hand side of a half equation with an electrode potential of 1.81, the largest in the series. And the iron 2 with 6 water ligands is up here with a smaller electrode potential, and it's on the right hand side of this half equation. We don't use this one up here because the water complex ion is on the left hand side, and so that definitely wouldn't react with another oxidizing agent down here. And so the language that we need to use is just to simply talk about the magnitude of the electrode potentials. And so we can simply say that cobalt 3 has a greater electrode potential than iron 3 plus. The equation, therefore, will be looking at moving this equation in the forward direction and this equation in the backwards direction. Now, both of them involve the transfer of 1 electron. Cobalt is gaining 1 electron and the iron complex is losing 1 electron. And so, very nicely, we don't need to multiply either of these half equations together. And so we need to therefore just write cobalt with 6 water ligands with a 3 charge overall reacts with the iron 2 complex and turns into the cobalt 2 complex and the iron 3 complex. And so overall the cobalt has been reduced by the iron. And then the last part of this question says, suggest why the 2 cobalt 3 complex ions in the table have different electrode potential values. Well, the 2 cobalt 3 is cobalt with 6 ammonia ligands and then a 3 charge, and cobalt with 6 water ligands and a 3 charge. And so in fact, quite simply for this question, we just need to say that the cobalt 3 has got different ligands. With the ammonia ligands it will have one colour, and with the water ligands it will have another colour. This question is about the development of lithium cells. The value of the electrode potential for lithium suggests that a lithium cell could have a large EMF. And the table below shows some electrode potential data. We've got 3 different half equations shown here with 3 different electrode potential values. Use data in the table to explain why an aqueous electrolyte is not used for a lithium cell. Well, the top half equation will be the equation that has to be present for a lithium cell, and you can see here that we've got water, which is the component that makes something aqueous. And so if we look at these half equations, the electrode potential for lithium is very, very small. That makes sense because lithium ions are very poor at taking electrons. They're far better as lithium atoms at donating electrons. And then the water's electrode potential is larger, still negative, but much larger than lithium's. And so what would happen is the lithium half equation would go backwards, and the water half equation would go forwards. So in other words, lithium would react with the water present in the electrolyte. And the reason that we would need to say for this to get our second mark, because this is a 2-mark question, is simply that lithium's electrode potential is more negative than the electrode potential for water. Or you could also say that they would have a positive EMF of the difference between these two numbers, which works out at 2.21 volts. In B, it says, in the 1970s, lithium iodine cells became a common power source for heart pacemakers. Lithium iodide is the final product of the cell reaction. Use the data in the table to calculate the cell EMF of a standard lithium iodine cell. To do this, well, I've already just said actually, we need to find the difference between the two electropotential values. Obviously, this time we're using iodine's half equation and lithium's half equation. The iodine is the larger number, so it's always the larger number minus the smaller number, so 0.54 minus 3.04, which gives us an EMF of 3.58 volts. And then the last question on this page says an EMF value for a commercial lithium iodine cell is 2.8 volts. Suggest why this value is different from the value we've just calculated in part B of 3.58 volts. Well, the only answer we can possibly suggest is that there is something different about the conditions. When we calculated that EMF in part B, we used the electrochemical series, and specifically we used these electropotential values which are taken under standard conditions. So the best answer for 9C is to simply say that these are non-standard conditions. In some lithium cells, lithium perchlorate, LiClO4, is used as the electrolyte. Deduce the oxidation state of chlorine in LiClO4. Well, to deduce the oxidation state of anything, we need to do two things. First of all, we need to acknowledge that the sum of all of the oxidation states of all of the atoms is equal to the overall charge. Well, LiClO4 doesn't have any charge. That means these oxidation states add up to 0. Lithium is in group 1 of the periodic table, so its oxidation state will be +1. Oxygen is in group 6 of the periodic table, so its oxidation state will be -2. And so then what we need to do is say that lithium plus chlorine plus 4 oxygen equals 0. So +1 plus chlorine minus 8 equals 0. So chlorine must be +7 for its oxidation state. In other lithium cells, lithium cobalt oxide electrodes and lithium electrodes are used. Give an equation for the reaction that occurs at the positive lithium cobalt oxide electrode. Now this is one that you just need to remember. The lithium cobalt oxide electrode has got the following half equation. It's got a reaction between lithium and cobalt oxide, as the name implies, and in that process one electron is gained. Remember, we always write this in the forwards direction. And when that happens, we make lithium cobalt oxide as one combined substance. Alternatively, you could keep those separated in the products, or at least keep them as being acknowledged as being ionic. And so you're writing Li plus CoO2 minus. Either of those is fine. I prefer the top one. And then the final question says, give an equation for the reaction that occurs at the negative lithium electrode. Well, we saw in the previous electrochemical series that lithium is an electropotential of -3.04. And so it's going to be going backwards. And so that means that solid lithium is going to turn into lithium ions and in that process lose an electron. And so we need to write Li turning into Li plus 1 electron. And that's all necessary for the 1 mark. Okay, that's the end of this question and that's the end of this video. I hope it was useful. I'll see you again soon.